Good evening, everyone. So the topic of my presentation is neural network-based positioning system for localization and 3D shape detection in crowded IoT networks. I'm Rishu. I'm a postdoctoral fellow at Trinity College. Basically, in this work, we have used visible light communication as a communication medium to enable a positioning algorithm which can detect the location as well as estimate the shape of any object that is mostly people present in an indoor environment. First I'll start with an introduction to VLC. VLC is basically a short-range optical wireless communication technology, and it operates in the frequency range 400 to 800 terahertz. And it's mostly based on LED lighting, although some research has also started to use researchers have also started to use visible light lasers, but that does not include illumination functionality. So basically, by definition, VLC should be operating on LED lighting, and it can provide both illumination and communication. So the next question would be why to use VLC? So VLC already benefits from the advantages of LEDs. We all know that LEDs are more efficient and they are beneficial over the other lighting technologies. That is why all lights these days are being replaced by LEDs. And there is a very strong potential market for LED technology, and it can supplement and also substitute sometimes the RF spectrum. So basically, VLC can be used in conjunction with Wi-Fi, and it does not need any separate routers like Wi-Fi does. And it is a green technology, so it is more efficient, and that is why there is a push towards going towards visible light communication in the indoor wireless communication domain. And the next topic would be that why we are using visible light based positioning system. So in indoor localization, VLC will provide more accurate and precise location as compared to Wi-Fi, because the number of LEDs is approximately 10 times more than the number of Wi-Fi access points in an indoor environment. So as the number of access points is more for VLC, so that they can provide more accurate and precise localization. And also the beam divergence of LEDs is less as compared to the RF transmitters. So that also helps in providing more accurate results for positioning systems. And as I already mentioned, that VLC has some advantages over RF communication. So any technology that is using VLC also benefits from those advantages. Then coming to the objectives and contributions of this work. So in this work, we are trying to predict the location and estimate the shape of obstacles present in a crowded IoT sensor network that is mostly deployed indoors. And for that, we'll be using a shallow neural network, and which will be trained based on data collected from a VLC-based communication system. And then we will determine the errors in the localization and shape estimation predicted by the design and neural network technology algorithm. And then we'll also analyze the effect of some system parameters like grid size, and if there are multiple obstacles in the room, so how does that affect the performance of the neural network-based visible light positioning algorithm. So let's start with the system model. So this is a basic indoor environment where we have shown 4 persons in a room. The room size is here, the length and breadth X, Y, and height is Z. Normally, this is 5 meter cross 5 meters on the floor and 3 meters high. So this is the conventional setup that we use for testing VLC systems. And these the 4 bulb-like structures on the ceiling, they are the LED transmitters, and they act as signal emitters in case of VLC. So any signal that is coming from an LED, it can reach the user as a direct line of sight path, and also it can get reflected from walls, which will lead to the existence of non-line of sight paths. So we have to model in our work. We have modeled both these scenarios. They can also be more than 1 or 2 reflections, but previous studies and in literature, we have in our own work we have shown that reflections crossing above two reflections. Those signals are very weak when they reach the user, so they do not affect the overall performance to a very large extent. So in this work, because our main focus was on positioning and not on communication, so we we have only considered up to one reflection in the system. So to model these two scenarios, for the line of sight gain, the expression is given here, and also for the non-line of sight channel gain. So the total gain for any user would be the sum of these two. And using these equations, we have obtained the power profile across the floor in an indoor environment and use that power profile to train our neural network. And then because in this model, there is no consideration of obstacles. It only considers the presence of walls of the room. So we have also modeled the obstacles. So obstacles are modeled as cylinders here with height HB and diameter dB. So this is basically human body can be modeled as cylinder. And then using that, we have shown that we have assumed that in the shadow of the human body would be a cylindrical area that would be given by dt minus dB into capital dB. And using this, we can determine the area across which there will be a communication blockage if there is a person standing in between the receiver and the transmitter. So in this way, we have modeled multiple obstacles in the room. So other than the person who we are trying to locate and estimate the shape of, other than that, all other persons in the room are considered as obstacles. And now I will explain the neural network prediction model that we have used. So we have used a shallow neural network, as I already explained before. And for this study, we have used 576 input features. These input features are basically the received power profile that we receive on the floor of the room. And then there are 10 hidden layers and one output layer. The output feature can be either, depending on what we are training on, it can be the location or the height or the radius, which helps in determining the shape of the object. So these are the results when we're trying to train the neural network, and we have also given the regression values here. So the regression value, the higher it is, the more closer it is to 1, it gives us a better training accuracy. And we have first started with the training the model, and then we have validated it, then tested it on the real, like on a test case scenario. And for all these, we have obtained satisfactory regression values. And then we have run it for approximately 100 epochs, and then we have shown that the threshold for minimum validation RMSE, which is approximately, I think, around 0.01, and for that we determined that if we run the training for 96 epochs, it gives us satisfactory performance. And then we have evaluated the performance of the neural network prediction. And for this, so these are the errors in location estimation for two different cases. So on the left side, we have shown the effect of the grid size. So this grid size is basically the size of the grids that we have assumed the floor to be divided on. So in each grid, we have placed one receiver on the floor, and but the grid size, it affects the performance because the lower the grid size, we will get a more precise estimation of the location, but that would increase the system cost. So there is a trade-off, obviously. And then when we increase the grid size, as we can see here, that the error in location, it increases. But we have also observed here that when increasing the grid size to 0.2 meters, the change in error is not much. So we settled that we will use for all practical purposes, we can use 0.2 meters as a grid size for a 5 cross 5 meter room. And on the right side, we have shown the effect of obstacles. So as I said earlier, that the person who we are trying to locate is considered as the user, and all other persons in the room are considered obstacles. So when we start with 2 obstacles and increase it to 10, the error in location it increases as expected. And but still it is not a lot, because The highest error when we increase it to 10 obstacles is around 0.2 meters, which is very less for a room size of 5 cross 5 meters. And in a room size of 5 cross 5 meters, we do not expect there to be more than 10 sensor nodes or persons in a room size of 5 cross 5 meters. So this gives us a satisfactory performance. And then when coming to the shape estimation, so the shape comprises of height and radius, as I mentioned before. So here also, as we increase the number of obstacles, the error in estimation is increasing, and the general shape that we have considered for a human being is around the height to be around 1.5 meters and the radius to be around around 100 centimeters or so. So that in that sense, the error is the percentage error is very less, even when the number of obstacles is increased to 10. And combining the radius and the height, we can determine the shape of the object that is present in the sensor environment. So these are the conclusions of our work. We have proposed an Anand-based algorithm that can estimate the location, height, and radius of objects or people present in the IoT sensor network. And we have trained the neural network and seen that the location error is satisfactory. The location error is approximately 0.548% for a room size of 5 meter cross 5 meters. And when for the height and radius, the highest errors obtained are 4 centimeter and 1.3 centimeters respectively. And we have also examined the effect of increase in grid size and the number of obstacles to analyze the performance of the neural network-based visible light positioning system. These are some of the references that we have used in our study. Thank you.